Hello, everyone. Welcome to our panel on challenges in productive and sustainable software for Exascale and beyond. My name is Lois Curfman McInnes, and I am co-moderating this panel with my partner, Rich Brueckner. I'm a computational scientist at Argonne National Lab, and my background is scalable numerical software and issues in interoperability among software developed by different teams, as well as issues in software productivity and sustainability. Today, we will have a conversation with our international experts on various aspects of software, and we'll begin by each one of them introducing themselves. So first, Satoshi Matsuoka.
Okay. So hi, I'm Satoshi Matsuoka. My current affiliation is RECAN. RECAN's the Center for Computational Science. I'm the director there, as well as I'm a professor at Tokyo Institute of Technology. And had a very long career in this business, but I'm basically a systems guy. I've been building, both in software and hardware. I've been building systems like Tsubame series of supercomputers, to our pioneering GPU systems. But now I'm responsible for the K computer and then the next generation Fugaku, the post-K Fugaku supercomputer, which will be one of the first Exascale systems in the world. And we'll have more than 150,000 nodes, or about 8 million CPU cores.
Thanks, Satoshi.
Yeah.
Next, we have Michaela Toffer.
Thank you. I'm very excited to be here. My name is Michaela Taufer. I'm a professor in electrical engineering and computer science at the University of Tennessee, Knoxville. I come from the computational science, simulations of molecular dynamics, and I moved through the process that many of us are moving through from compute-intensive to data-intensive applications, aspect of in situ analytics and non-determinism.
Thanks, Michaela. Peter Bauer.
Thanks very much. My name is Peter Bauer. I'm with an international organization that sits in the United Kingdom in Reading. It's called the European Centre for Medium-Range Weather Forecasts. So I'm obviously representing weather and climate prediction as an application here. We have a big supercomputer as well because we operate under very tight schedules. At ECMWF, I'm the Deputy Director of the Research Department, which is our biggest department. We need to do a lot of research to produce accurate forecasts. And I'm leading a very large effort on scalability, as we call it, which is basically all the computational science around our application, the computational aspects, the data aspects, and the workflow aspects.
Thank you. Hao-Huan Fu.
Right. So I guess you should still remember me from the morning. My name is Hao-Huan. I'm from, also from Tsinghua University and the National Supercomputing Center in Wuxi. So my job at the center is the deputy director in charge of research and development. So basically writing software for Sunway Taihu Light. My background, most of my education is in computer science, but I'm a professor in the Department of Earth System Science. So a lot of my efforts are actually trying to use HPC to resolve Earth science-related problems.
Thank you. Rich.
Well, I'm very humbled to be here. I don't know if you folks know me, but I'm a reporter for insideHPC, and I've been coming here for a number of years. But if you're wondering why there's two moderators, I'm here to get stories. And as a storyteller, you're all going to get to participate today. At each of these seats, every other seat or so, there's a microphone. So we have some prepared questions that Lois is going to ask, and at about the 30-minute mark, we're going to ask you to participate, and we'll raise your hand, and you hit a button on there, it turns red, that means your mic is live, and we want you to tell us your stories, ask the panel what's on your mind, and at the very end, we're going to share some logistics about the evening dinner event. So with that, Lois, I think we should get started.
Thank you. So as we've already been discussing at this conference, software is a key cross-cutting technology by which we do computational science. It's the way in which we collaborate and encapsulate expertise across mathematics, computer science, and various domains in science and engineering. Our challenges in software are getting more and more complex as we're dealing with disruptive architectural changes, increasing demands of our software to tackle multiscale, multiphysics problems, to incorporate both simulations and data analytics, and likewise to have simulations that are reproducible as well as sustainable. So today, our various panelists are going to speak about some of their experiences in this space. So we'll begin by asking each panelist, what do you consider to be the most pressing challenge in the space of software productivity and sustainability, both now and in the future, Exascale and beyond? Satoshi?
Okay, so that topic has been actually one of the central topics during my career. I'm a systems person, both from software and hardware perspective. And the challenge has always been how to balance the ecosystem. The important, ecosystem is very important. That's in software, and of course, everywhere. And that's not just with HPC, but how to sustain the very broad software ecosystem versus trying to pursue the bleeding edge. And and if you do too much of the latter, what will end up is you just die. So there's a very interesting web page, that supercomputing vendor page, if you search Google. And you get a list of this whole list of vendors that have passed away over the years. And the reason they passed away is predominantly because the software ecosystem, they couldn't create the software ecosystem to sustain the overall business. But if you do that too much, what happens is you get a very underperforming system because you'll be just buying into this very vanilla thing. And thus, you no longer are in the supercomputing realm because that's the whole purpose of supercomputing, to achieve performance. So this duality of how do you have this really very rich ecosystem versus how do you pursue the bleeding edge? And so a lot of my efforts in the past have been to how to realize both at the same time. And I can give more exemplars, but I'll just pass it on for the interest of time.
I think we need to sort of have a 360-degree vision of what is that our software does. We started 10, 20 years ago thinking about software as a simulation of a phenomena, and we were sort of focused on one single aspect, which was the simulation itself. And now we look at what our workflows are becoming, and it's such an heterogeneous path towards science production and discovery. And so it's no longer just a single architecture, a single package, but we move from compute-intensive to data-intensive stages, and we have to plug them together to work. And it looks easy. It looks quite trivial, but then when we do that and when we share that with others, that is a big challenge. And I think that if you start looking at what the workflows are becoming and how we need to integrate them, we need also to change our state of mind towards what is that we are doing with our software. So I think that is a big challenge.
I probably have to give an answer slightly from an application point of view. I think in the past we have been spoiled by general purpose chips, general purpose architectures, general purpose compilers, everything worked for, and programming standards, everything worked for us. We could just afford to run our application with 5% sustained efficiency on computers and still buy them and run them and fulfill our scientific needs. So while we have a very good idea of where we want to go science-wise in the next 5 or 10 years, we don't know where the technological evolution is going to get us and whether it's actually supporting our scientific ambitions. And there were 2 sessions today about weather and climate, and I'd say at least 80% of the contents of the talks were actually about how to overcome this and take things in our own hand. So on this domain-specific language, for example, buzzword, we only started to think about 5 years ago, is now in everybody's talk. And there's actually living examples of how to do this. But that implies as well that there's actually a load now, a development load on us to take care of ourselves rather than rely on external factors just delivering this to us. And the number I can give is at the center at ESMWF, we have great staff, excellent staff, but we probably had like 2, 3, 4 people max taking care of code optimization and adaptation. Today, with the work we're investing in developing our own, taking care of ourselves, it's at least 20 people, 25 people, you know, and that is reflected in many other places as well. So you have a shift of responsibility because of this lack of natural evolution of standards and common technology.
Right. I didn't know we speak in the sequence of the seats. Otherwise, yeah, I would follow up on the application side, actually. So the first sort of piece of code that we try to put onto Sunway Telco Lite is the CESM, this Earth System model, with over 1 million lines of code. And so after that, you can imagine it's a very frustrating process. We have roughly 20 students to go on the projects. And after 3 months, I think only one still would like to continue. Because I forced him. He's my student, so I can.
You own him.
So actually, after this, I was thinking, the toughest challenge is actually we don't have students or say engineers with a multidisciplinary set of knowledge and skills. Because when they look at this 1 million lines of code, they don't understand. I mean, Peter can understand this. It's about cloud. Not that cloud, it's the real cloud. Or, typhoon or interesting phenomenon that you want to study. But for computer science students, after 3 months, they will come to you and saying that deep learning is very sexy. I want that. So for me, I think the talents that can really understand both science and engineering is probably one of the challenge that we're going to face.
Absolutely, yeah. Do you have follow-ups at this point?
Well, real quick, I wanted to revisit this idea of ecosystems, because Satoshi, the K computer that you're going to supplant with the Fugaku
Yes.
machine was kind of a one-off, right? It was a Spark machine with Linux, and it might have been the only one in the world.
There are lots of species of Linux in your previous company.
At least for HPC, right?
Yeah.
And now you're starting with ARM, which is not exactly a big presence on the top 500, but you're going to have a machine of incredible scale, but has its own ecosystem outside of HPC.
Right.
Right? What is the challenge there?
Well, the challenge, of course, the first challenge was convincing everyone, right, that ecosystem was of grave importance. Because the Japanese supercomputing vendors have had a long history of, not necessarily the computer vendors themselves, because if you look at unwind the history of Japanese computers, they've always created like IBM compatibles, right? And then they got sued, so there were a lot of stories about there. Yeah. So despite the fact that mainstream computing, the Japanese vendors have been creating basically like copies of IBM and stuff, and also like microprocessors. For HPC, for some reason, they had always committed to building some proprietary stuff. And this continued for many years.
Yeah.
So it took a lot of effort to initially try to convince a partner like Fujitsu to say we'll go ARM. There's a heated discussion. And now that was done, then of course the second challenge is, was to how to come up with enhancements of ARM, ISA, and the microarchitecture, in order to support HPC workloads. And there were a lot of initial trials to try to adapt mobile processors in the ARM space to be used in HPC. For example, the Mont Blanc effort in Europe, and we had our own efforts, and there were several other efforts in the world. And of course, the foregone conclusion was that was not going to happen, because inherently it was just, for various reasons, it was just too hard, because these mobile devices, for various reasons, were not tailored to run at scale. So then we had to go through all the exercise of how to add these features onto to come up with a brand new microarchitecture, but brand new instruction sets which are turned into SVE, and then also have HPC enhancements like putting HBM2 on the stack, just like GPUs. That's the second challenge. The third challenge, of course, despite this very broad ARM ecosystem, in the other, in this space, in the mobile space, there are some tools which still needed to be ported over to HPC space. There are some unique requirements like MPI or parallel file systems, or some of the debugging tools, and also SV itself, how to come up with optimized SV libraries. So there are challenges there. But overall, I think once these challenges are overcome, we'll be at the very tip of this very humongous ARM ecosystem. And it's nowadays, because of security reasons, become very important that the code would run ubiquitously from the edge all the way to the cloud. So this very same code will run from the edge to the cloud, which will be an inherent advantage in the ARM ecosystem. So I think we have a pretty good solution, actually, in our upcoming system.
Thanks. So already our panelists have talked about multidisciplinary collaboration, ecosystems, teamwork. I wonder if you could comment about whether some of the aspects of the culture and the reward structure in high-performance computing and computational science either help or hinder some of those challenges that we're encountering. Why don't we start at the other end?
I think his answer was...
That's very unexpected. Yeah, actually, so I think we had some of the culture issues. Like, I think in each university, the president of the university would say, you have to collaborate with different departments. But then after you write the paper only goes to the credit of one single department. So after you become, let's say, after you write a good paper and then the department heads start to fight and then they become angry with you. So that's the part currently not working very well. We were proposing to the president, you should just give double credits to all the departments related. But currently it's not like that. And also there's one thing. So Satoshi was talking about actually the basic software, like the compiler, the operating system, is actually a problem in China now. If you look at the universities, there used to be good professors doing research on that. But it's very difficult to write papers for compilers or operating systems. So nowadays we don't have many professors doing that. So that's also another part of the problem. How do you evaluate your research in terms of HPC-related software?
Yes, those are challenges. Peter?
Well, again, application-oriented response. I think in our case, a lot of the reward comes from what science you can actually implement. That applies equally to the applied scientist, the person developing the cloud scheme, as to the computational scientist, because if you happen to improve the forecast by a certain factor, you can see the result every day. It saves lives, actually. If you happen to be able to prepare a weather prediction system for the next generation of supercomputers that looks entirely different than today, and you can do that on time, you save money and lives again. So I think that is why we're actually seeing, maybe opposite what you said in your first statement, is actually that I think we can actually see at the interface between our science, the applied science, and the computational science, a new generation of people coming from aerospace engineering or other disciplines that have backgrounds in fluid dynamics, but at the same time are very good computational scientists coming into our discipline, because they understand that weather and climate prediction has a great societal impact, and they have a conscience. They don't go to Google, they come to us, and they really want to improve the system. And apparently, working in that environment is very rewarding. So I can see actually in our field that there's obviously enough incentive and reward to draw people in and build up that interface that didn't exist before.
I think we are in a sort of critical time in which we need probably to pause a moment and think about how we evaluate the contribution of computational scientists when the research is in between computer science and sciences. I think that what several of us may have experienced, that we submit paper and we get back review that tell us, oh, this is engineering, or you are not really HPC, or you are not really computational chemistry. We need really to pause and understand that putting together workflows, generating real science, it's not trivial. And describing how to achieve this process is a contribution. So several of us who review papers, who assess the quality of our colleagues, should be more careful in assessing work as trivial, because there is not a mathematical formula. And I think it's a transition that we need to do, because otherwise we will lose this opportunity of really on a long-term collaborate.
Yeah.
Okay, so when I became director at RECAN CCS, so I try to restructure our directions a bit, because we were a little bit too focused on the simulation outcomes and not broad enough to be a more broader HPC, part of the broader HPC ecosystem. So my question was, what does RECAN Center for Computational Science, what does computational science mean? So we said, well, we're studying computing, obviously, and we're doing science about or related to computing, because our key element is computing. So I said, well, we should strive in pursuing science of computing, meaning that we should, and especially high performance, because that's what that's a subject matter of science. So we should really stress that. But also we say science by computing, because that's the more traditional computational science, where where the outcomes of studies of computing will actually drive other sciences. And science for computing, there are other scientific disciplines which would contribute to computing, like material science for new devices, so on and so forth. And so we should collaborate with those. So together, science of computing by computing for computing, which is kind of a stealing a little bit of a quote from when U.S. presidents were very honorable, and not computing first, something like that.
Sure.
So that's the direction. Now, as for the reward structure, if you keep that in mind, I think the reward structure, has become quite enriched in the recent years, because that really tells you that we're involved in a very multidisciplinary area. And actually, there's a very high demand for people of those skill sets. And whether they become scientists or they start working at Google, that they have a very flexible career path. And as such, and very high demand, as such, very high reward, be it financial reward or some reward in some prestigious scientific institutions or whatnot. I think there's a very the reward themselves are quite enriched as compared to the previous years. And this interest in computing has, I think, really have changed the value systems of the young people at large. Because in Japan, there was a recent poll. We asked the junior, like 13-year-olds, what do you want to become when you become an adult? So for a long time, people said, well, we become a medical doctor. I want to become a baseball player or a soccer player, for that matter, or things like that. But now the top #1 ranking professional is an IT professional. So that, by the way, #6 is a YouTuber, so you have to take it with a little grain of salt. But actually that will accumulate talent. Basically, when people aspire to be the best talents aspire to go into that field, then you get very rich sets of talents. So if we sustain a proper reward system such that no matter what they do, being engulfed, being exposed to this multidisciplinary area, to the extent that they have a very rich career path, I think I think we will have a very promising future. We just have to make sure that not all the people go work for Google, and we retain a little bit of talent for ourselves. Yeah.
I would like to agree and disagree with you, Satoshi.
Disagree.
I agree with you that working in across discipline is one of the most exciting jobs that a person can have. I fully agree with you. I disagree with you that there is a community that welcome that. I think that today still we struggle to get tenures when we do interdisciplinary research. We still struggle to get jobs when we do and probably we make jobs in position like industry, but if you go in academia, it's still hard to make a career if you work across disciplines.
Well, so becoming a director at RECAN is an interesting one. Well, we have 15 centers at RECAN, okay, and it's a very interesting experience career. It's much more interesting to some extent than being a professor at this point. Although I'm still a professor, the reason is, there are 15 other centers, and half are like something related to biology. So you get to basically converse with a lot of these directors, some of who are like Nobel Prize candidates, and they're very esteemed people, but they complain a lot about their center. And one of the complaints they have is one of the things I found out is, for example, biology has a completely different type of value system as opposed to physics or computer science and whatnot. In fact, in biology, a lot of people are very narrow. Extreme. I don't know if you have biologists. I'm sorry if I've offended you, but very narrow skill sets. So they cannot. It's very hard for them to change their career, especially when you're experimental. So compared to that, I think we have a very broad. People's skill sets are broad. So I don't know why they're having such problems finding good jobs.
It's not the problem in finding good jobs. It's sometimes a challenge in move forwards in careers, especially in environments. I know not everybody has the luck, the fortune to work in a very dynamic environment. A lot of institutions still are small and have traditional criteria for assessing the success of our students, the success of our faculty, and even the success of papers. So we need to learn to be more open-minded and reevaluate what is success in these careers. It's not an H index, which sometimes is not as high as people that work in a single field. It's not a single paper, but it's this bringing vision. And how do you measure visions in a community that is interdisciplinary?
Sure, that's particularly challenging, I think, as we think about software and the many contributions we need to have to make effective software, as Peter talked about.
You work at one of the top university in China, so do you have similar problems?
Yeah, I think it's especially, so for me, I kind of resolved my issue because I demonstrate that I can use HPC to solve problems that they cannot solve. But still, when I go to the next level, it's like McInnes said, I don't know whether I should compete with people from computer science. They would say, you are from Earth System Science Department. If I compete with climate scientists, they would say, you are a programmer. You are not a scientist. So it's this...
But why do you need to compete? I mean, isn't it more like that you have new disciplines coming up at exactly the interfaces I mentioned before? It doesn't need to be, you don't need to invade a computational scientist or climate scientist area. There's new areas coming up at the interface that didn't exist at all before. It's a new type of expertise, and therefore there's new dynamics and new incentives and new career paths.
Yeah, I definitely agree with that. As Michaela also mentioned, if I give up and I start up a company to do all these things that I can do, it would be quite rewarding. But in university, it's still not. They make very clear categories. You have to fall into one specific category.
And there's funding. I mean, in the end, funding is the driver for a lot of that.
Funding is a big issue.
If you can supply the funding for what you want to do, it doesn't matter what you want to do.
But
and there's big funding programs. So
that's one of the issues.
Happen.
But I want to go back to the software aspect and describe a small personal experience. I report in my CV some of the software that with my group we developed, and I have a department chair asking me, why do you report the software in your CV during an annual evaluation, which is because it's a product so there is the culture of software not as a product. Few of us are able to associate a DOI to our software and distribute that, and that is something that we should do more.
Yeah. Well, you moved to a new university, right?
Yes.
Yeah.
Precisely for that reason.
Same for data sets, you know.
Or data set, exactly. Can we put DOI? Can we assess them?
But that
as a
exists now, you know, so the infrastructure is there.
I think, but I think there is a, you know, because I'm on these government committees and all that, and I think at the very top level, there is a growing recognition for example, need for open science and thus open data sets. And of course, we advocate for them. And the people at the very senior level, also bureaucrats and so forth, they do understand the needs. So maybe it's people who are kind of stuck in the middle, the old people who have very solid mindsets who will probably retire pretty soon. Mm-hmm. And hopefully, and then we have a very brave new world where I think these multidisciplinary work values, and in the new world, in the new realm, will be well evaluated. And I think and we can sort of being very forward-looking institution as opposed to universities. National labs are more dynamic. I'm seeing this tremendous change in the culture thing.
All right, folks, well, we're up at the halfway point for this session, and I'm a reporter, so I have a million questions, but we want to make this participatory. So if we have questions from the audience, please raise your hand. There's going to be a microphone. We ask you to use that so that the camera can hear you. So first, who has a question for our panel today? Don't be shy, right here. Red is on.
Okay, now it's right. Now, actually, the subject of the discussion was exascale and beyond. Then we just went to the careers, and these careers of numerical scientists is not very estimated, it's not very nicely founded. And I'm coming from fusion community, it's exactly the same problem we have, exactly. Because physicists are kind of have careers, they have publications, but people who are doing codes or optimizing codes. And now, what I see already, what's going on in Europe, because you're presenting many countries. We used to think in Europe that in Japan it's good, in China it's very nice, in a way that there are people and there is funding to adapt existing, for example, codes for applications to exascale, and architectures are developing together with codes and applications. And now you didn't mention it at all. I wonder, what do you think? For the moment, we're just looking at these tendencies that people are doing exascale, like based on GPUs, RAM, or something. But nobody is listening to us to use this, because, for example, if it scales badly, what we can do, and stuff like this. I would like to hear an opinion of somebody. Can you comment on it? Because you're talking about applications. But now we are doing architectures kind of independently, going to exascale.
Well, that's not
of applications,
kind
of.
That's completely untrue. That's completely untrue.
No, it's completely untrue maybe in Japan, but it's more or less like this in Europe, and we worry about it. I'm in PRAISE scientific steering committee, and we worry about it, and scientists would just keep talking about this. And so what do you think about it? Is it because of fundings? Is it because of organization? Or what kind of efforts we could do to join the development of high-performance computing and applications?
No, I think I understood what you want to say, but please correct me if I didn't once I start. I think partly what you're saying is true, and we had a very big discussion in Europe over the past 5 years in the context of, you know, where large European infrastructures that are eventually, or in part, managed by PRAISE, for example, should go in the future, and how do we get the applications along, and are these architectures actually at all designed to fulfill what the individual applications need? And again, I think the level at which that started was, again, in the old school thinking of, we have a general purpose machine, it's flop oriented, as long as it's high enough in the top 500 list, it should be all right. and then we make a separate effort, probably underfunded, to get the applications on it, and you know, they just achieve the same performance as ever. I think that's how it started. I think that's slightly changing now. I think there are increasingly there's an increasing awareness, for example, at the European Commission level, but also at national level, because for those of you who don't know, it's a co-funded effort. So there's a big European united investment, and that is complemented by individual national funding, which is a complicated thing. But this is democracy. So in any case, I think there is a step or movement towards getting increasingly domain-specific, to recognize where the individual domains suffer, to maybe really invest in co-design and not just try to optimize and adapt applications for pre-designed HPC systems, but to help them along at least at system level, if not at component level. So I think it's actually coming along, and I hope that maybe not for the pre-exascale systems, but for the ones after, or even the ones after, we will be in a different place where we have not just 4 or 5 machines of the same type, but 4 or 5 machines that serve specific application groups that share the same problems. So you have different flavors of technology that is available, and maybe in part actually co-designed to serve applications better, groups of applications better than today with the general purpose machines. I think it's moving.
And I can add something related to the United States. I've been asked to advise some university on what to do when they try to improve their HPC system. And the attitude is to start with the big machine. But as this university goes through surveys, that they reach out to their scientists, who are the ones that are listening in this case, it comes clearly out that it's not a single machine, that it's better to invest in more domain-specific machine and embrace a group of scientists or domains. So there is some movement in that direction. Of course, there is still the old-fashioned tradition of the big top 500. And I think that there is a shifting also in that. Oh. Takes some time.
Oh. So, you know, when crosscutting was developed, so basically the first thing that was ditched from the objective was to do well in the top 500. That was the first objective that was thrown away. Okay. And the whole project started around 2009, even before K, the K computer. So there was initial studies of the possible architectures in the 2020 era timeframe, and you know, possible alternatives. And then the next phase that happened in 2012 was to basically start a set of what we called a feasibility study project, by which we involved all the Japanese application community, like in its entirety. Everyone, basically, well, everyone who's been using big machines. Not 100,000 people, but at least people who are using supercomputers. And to get them involved in the co-design process. And there were 4 teams, and I was responsible for one of the application teams from the system perspective. And what we did was to basically group all the people, all the stakeholders in a single room. And then in a short version, we forced them to write a 600-page report on what would happen, what are the science they project 10 years from now, 5 years from now, 10 years from now, and what are the computational capacity requirements, what are the algorithms they'll use, and so forth. So if you look at the report, and the English summary, 60-page English summary, 600-page Japanese version. And you know, you get the whole chart of the applications and the computational requirements and the scientific outcome. And then based on those, the POSCE Fugaku project was officially launched in 2014. But at the same time, it wasn't just a machine development project. The 9 priority areas, priority areas were selected. And each of these areas were asked to come up with 1 representative co-design targets. So and there were 9 areas, so 9 co-design targets were chosen. And the whole design process was basically to achieve up to 100 times performance boost, given the capacity requirements. 100 times performance boost when the average of about 40 over K for each of the areas. And it's projected that, we know, in fact, we know now because we have the real chip and everything, we will achieve this goal. So, it was a very orchestrated process, co-design process, by which we developed post-K. It was not to hit the top 500. It was not to boast plots numbers. It was not to take off-the-shelf components. All the components are new, freshly designed, optimized for HPC, and listening to all the application requirements.
Well, Lois, you manage a huge team of people preparing for these exascale machines. Are you seeing this kind of frustration out there, or are you working to fix that? What would you say?
Well, so I work in the Exascale computing project, in particular coordinate work in math libraries, where the math libraries teams all collaborate with scientific applications. And I would say that we've been very pleased and happy with the multidisciplinary collaborations that we're seeing. And we're making some good steps forward in co-design. I will say that we're still challenged, though, I believe, in terms of collaborative software to develop appropriate career paths for everyone who are participants in our broad teams. Research software engineers are incredibly important for the work that we do. And I believe as an international community, there's lots of opportunity for all of us to work together to make sure that we can fully support our broad skills that we need in order to do collaborative computational science.
Okay. Did that answer your question? Okay, yeah. We have another right there. Got the mic. Red is on.
So I do experimental high energy physics. And from our point of view in the community, the next generation and the generation after that probably of HPCs is an utter and complete disaster. Intel has told us, don't worry, we'll help you port your code to A21. NVIDIA has said the same for Perlmutter. I'm sure AMD will tell us the same for Frontier. We have millions of lines of code, and we cannot afford to port to specific machines every 2 years. Do you see any hope of convergence of technologies, either on the hardware side or on the software side, that will spare us from this? It's just an impossible burden, frankly.
I have an answer later.
Well, I think I mentioned it maybe earlier, but where I said that kind of in our community we're trying to take things in our own hand. I don't think there's technological convergence. I'm not sure you want that, actually. I think you want actually heterogeneous architectures because at least in our application, if we go through the big components that kind of cost the most in our system, they have very different patterns in terms of how they stress memory or what memory bandwidth they require or what data they produce and these kind of things, or what level of parallelism they actually allow or vectorization and these things. So I don't think you want actually one size fits all for that. So I think heterogeneous architectures is probably good, but the difficulty is, of course, programming the different types of hardware, and that's where I said earlier, I think we at least try to take things in our own hand and implement what's been mentioned many times before in many PASC conferences, the so-called separation of concerns, where we hide away or abstract away all these different dimensions of adaptation and optimization away from the science code, so that your actual native science code becomes independent from the hardware. And below, you develop a big middle layer. That's the part we have to develop ourselves. And just underneath, at the bottom end, you have backends that work for specific components on specific hardware. And that's exchangeable and ideally fully flexible. So whatever you're facing in 5 years or 10 years, been taken care of, and you don't have to touch your top-level code anymore. But we're, of course, not naive. We know this is very intrusive. It takes different thinking in terms of computational science. You have to re-educate your scientists. but they will have less opportunities to break the code because they will never see the bottom layer, actually. So there's, I think there's solutions to that, but it's not going to be easy, and it's probably not something you can do incrementally. It's not like in the past where you do little changes piece by piece every little year to your code. I think it's one big jump. It's really a quantum leap in the real sense. There's nothing in between.
And I would like to sort of ask a question back, which is, what are our measures of success? What are our metrics of success? If it is flops, yes, we are constantly running and rewriting and adapting. But if it is science, I think that it changed a lot the perspective of how to re-engineer software. It is not something that every time that there is a new processor, you have to go and run and rewrite everything. I think we need to change also our metrics of success. And it's in terms of science that we can achieve. Thus, if we look in that criteria, in that condition, the requirement to rewriting the software is so urgent every time we have a new platform.
Success for us means publishing a paper, and the DOE has told us that we cannot use these machines if we don't use the GPUs. So we cannot publish, we cannot produce science.
But the GPU is probably one of these major jump, and then the question is, do you really need the last GPU? We go back also to the fact of what...
We need a GPU, we need a computer.
Wow.
We need
Let's
something
speak
which
about
can do
accelerators
calculations.
in general.
Well, we'll get the Fujitsu CPU and... no.
Accelerators.
No, well, I mean, it's a CPU, but it, has... well, seriously. There's always, there are, when you kind of structure the problem in various ways, there are, most of the HPC codes are bandwidth bound, memory bandwidth bound. There are a few that are exceptions, like first principle molecular orbitals and some molecular and also molecular dynamics, and maybe like things like DFT. Maybe those are the 3 instances that are flops bound. But most of the other HPC codes are bandwidth bound. So how do you drive the bandwidth? Well, architecturally, there are like 3 options. One is YSIMD, which is like Xeon, now sort of rest in peace, Xeon Phi. And then the proper version of this, which is A64FX, which is done right, by the way. The ARM people say they got the instruction set right too, but that's a different issue. Okay. And then there's the SIMD style dynamic threading plus vector lengths, and that's the GPU. So no matter whether being it NVIDIA or AMD or now Intel, GPUs basically have the similar structure. And then there is the more of a data flow-like approach, which is something it's not there yet, but the CGRA variants have always been proposed, and maybe there will be one in the future. So there are at least 3 architectural variants, and how do you have a software that would cope for each one? I think that's something that this community has been tackling for a long time. There are some successes, like there are OpenACC, OpenMP. There are C++ variants that try to hide away some of these complexities, and DSLs that's been mentioned and so forth. So there is constant challenge from that end, and trials from those, and it's on some successes. And that's ultimately what we're striving for. But at the end of the day, when you have a legacy Fortran code you really need to run, then I don't think there's any other choice but to basically try to use architecture that's probably most fit for those types of codes. And because if you're not rewriting it, or at least not rewriting it in significance, and because you want to spend your time otherwise. In case you have to get the proper architecture with that. There's just no. So either you try to invest in software to adapt to these architectural variants, or you don't. So you just try to pick the best hardware. Now, I'm not going to say which one, but it depends on your code. But fortunately, I think these each of the variations are coming up to speed. So Intel was in lull, but they'll have their But now that there's Fujitsu chip, which will probably blow them out of the water, really, they'll come up with competing chips that will try to compete with the Fujitsu, because otherwise they'll just lose their business. Yeah, because on CFD codes, the i644FX is 4 to 8 times faster than Intel, and that's because of the inherent properties of the high bandwidth memory. So I'm sure Intel will come up with variants with high bandwidth memory at some point, because otherwise they'll just lose all their business there.
Yeah, I just want to add a few comments to that question. Actually, I was trying, when I was talking with the climate guys, they had the same issue. When GPU came out in, I think, 2008 or 9, right? And it's only until recently that climate community is starting to look at GPUs. So they don't want to change, right? But if you look at the problem from another perspective, it's actually a good, maybe for a few decades you face this kind of disruptive architecture change that motivates you to talk with computer scientists, right? It's a good way to promote interdisciplinary. Usually they don't talk to me. Now they have to talk to me because they don't know how to run the code on some way type of light or something like that. So, and the other thing is, I'm not sure in the domain of high energy physics, like in climate, I think it's good for a few decades if you really relook at the code and refactor it, because some of the codes are really written a few decades away and nobody can really read it very smoothly. So it's good to actually reconstruct the code after a few decades. I think it can be good.
We had a question from Sunita.
So I'm Sunita from University of Delaware. I'm also a faculty, so it's very nice to see a faculty on the panel. So I'm going to follow up with your comment, Michaela. We have heard so much about the need for applying computer science on real science code, right? And I recently had this fabulous conversation about RSE, Research Software Engineers. And I was relaying this to other faculty across departments, across universities, wherever I got an opportunity. The challenge I see is if a student were to do engineering kind of work, which is equally important, it is perceived as, oh, it is not novel enough. And it doesn't qualify to give the student a PhD degree because there's no novelty because it's engineering work. And I got such feedback, which I totally disagreed to, because we need software developers, we need research software engineers to do the kind of science. And there are a lot of national lab and center on the podium as well as in the room. How is it that we can communicate back to universities that PhDs in RSE is equally important than a PhD in computer sciences, but the subcategory being RSE is important because that's what we need at the end of the day, be it high energy physics or be it climate or be it any interdisciplinary science. So how is it that we can take the message from you and be able to communicate back at the university level that that's very important and cannot be neglected?
I'm in trouble. I actually think that there is even a worse scenario of what you are describing, that we are running out of PhD students who are talented because sometimes our institution don't understand these talents, but the national lab, research labs, industry understand and come and offer them fantastic salary. And we run out of excellent student who does work in software development, sustainability, and get a PhD and become faculties. And we may have also students that look at us and say, I don't want to become like you, I go and get money. So I think that is an effort that the entire community should do. I look at this is my first time in PASC, and I look at this community that has been flourishing so quickly, and I think that is a clear message that there is a need to create this community of PhD students who graduate with work that is defined as engineering or software engineering. And I think that conferences like PASC are a response and a solution to this kind of culture, to change it. So very pleased that PASC exists, and I'm looking forward to seeing more of PASC as a motivation for our work.
I think the science of research software is incredibly important, and that is one way to frame, I believe, Sunita, some of the points that you're making, and I see it as a huge growth opportunity for our community. Very, very strongly needed.
Can I make a comment? Okay, so, you know, supercomputers back in let's say 60s, like Cray 1, there was only a factor of like 3 to 10 difference between a normal computer versus a supercomputer. Right? Supercomputer is like only 3 to 10 times faster. Now there's several orders of magnitude difference. Right? So if you look at, like, again, POSCE Fugaku has more than 150,000 nodes. It has more like 8 million cores. So, which is just huge. It's, in terms of number of cores, it's bigger than a Google Cloud data center. So if you're in the application side or the system side, if you can't find interesting problems, right, on such an infrastructure, be it, it can be a little smaller, but it doesn't matter. If you can't find interesting problems to solve on a system like that, I don't think you deserve a PhD. So, yeah.
And I think we can find that. I think that is the problem, is having the outside community acknowledging that that is an interesting problem.
So I think it's really important to actually partner, for example, computer science students, to really partner with people who have problems on the application side and use these high-end machines to solve real problems. And there will be some real challenges on the computer side to resolve. So, and similarly for the other way around. So I think fielding these infrastructures actually is truly important to advance science, because otherwise, if you're working at scale, which is mundane, then you don't find these problems.
Well, folks, we're at a hard stop here because of an event. I see we have more questions, but I want to let's give a hand to our panel. I think they did a great job. And